Today, we're talking about next level simulation for SOLIDWORKS users, as if the structural and fluid dynamics that we can run inside of SOLIDWORKS weren't advanced enough. My name is Philip Morrow. I've been a simulation specialist with MLC CAD systems for over a decade, and today I want to show you some tools that we haven't traditionally had our hands on that are considered higher level Simulia products. To do this, I'm going to give you an overview and a little history of Dassault systems and the Simulia brand of simulation tools. I'll show you how 3D Experience can connect to SOLIDWORKS so users can access these tools, and do a deep dive into these tools on a real-world example of real SOLIDWORKS users. Now, I've been a SOLIDWORKS user since 2005. It was over 10 years before that when SOLIDWORKS first existed, and I wonder if you remember what year it actually became a Dassault Systems product. I really got to see it grow over the years, bring in simulation capabilities for structural analysis, for fluid dynamics, give us data management, toolbox functionality. All of these items have grown either in-house or been acquired over the years and came in this timeline. We've had simulation inside of SOLIDWORKS since back in 2001. Now, of course, we've been getting enhancements every year since then, and it's been growing stronger. And this is just one subset of what the Dassault Systems company actually owns. They're really a juggernaut in the space, and while they own the SOLIDWORKS set of tools, they own a number of others for data management and all sorts of things, including a very high-end finite element analysis solver through the Abacus software. They've had this since 2005, and traditionally this has been a standalone product, and if we ran out of simulation capabilities inside of SOLIDWORKS, we'd have to use a disconnected workflow and maybe save our SOLIDWORKS files out and take them over to a higher level sim tool like Abacus, and then we couldn't get the parametric updates and design updates that we all rely on as a SOLIDWORKS user. Well, that's not the case anymore thanks to 3D Experience. 3D Experience is really the central hub that can connect together all the different Dassault Systems brands. You'll notice here on the left of the screen I've got the SOLIDWORKS brand, and I've also got CATIA. We've got things like Exolete. At the bottom we've got Simulia. Simulia is the industry term for all the simulation tools like Abacus that come from Dassault Systems. So today I want to focus on two areas here, the design and engineering area, where the SOLIDWORKS brand is, and the simulation area, where our simulation tool sets are, and show you how 3D Experience connects these worlds together so we can have a parametric bridge and the design updates in a connected process that all SOLIDWORKS users rely on. And again, this is really done through 3D Experience, a cloud platform whose backbone is data management, but these big softwares, these juggernauts like SOLIDWORKS, like the Simulia brand of products, they're going to get installed locally on premise. The beauty of using the cloud and 3D Experience to connect these is it takes care of our data translation, our data management. So we save a SOLIDWORKS file up, it takes care of the file types, it takes care of the translation. We can open it in a different tool set, run our simulations, make a design change in SOLIDWORKS, see that design flow right in. That's really the magic of using the 3D Experience platform. So let's talk about these simulation levels. Traditionally, we've had SOLIDWORKS simulation as a finite element analysis tool, a structural simulation tool inside of SOLIDWORKS in 3 levels. You can see them here in red: SOLIDWORKS Simulation Standard, Professional, and Premium. And I feel that these tools are really great for any designer. Any user of SOLIDWORKS should find out how strong are these. Are we in the ballpark? Maybe you bring that up a little bit into more of an engineering role when you start talking about frequency and fatigue analysis, or get into nonlinear a bit when you get into Simulation Premium, but that's where our FEA functionality can run out. Well, now when we take this into Simulia through 3D Experience, there's a couple of more levels that bring us really to the Abacus solver running in the background with Structural Performance Engineer and Structural Mechanics Engineer. Let me break these down into some detailed functionality. I think of them in the 4 levels. Structural Designer would be a starting point. You can run your linear, static, and frequency there. Also get into some cloud solving if you don't want to use your CPUs to crunch the numbers. At the next level, structural engineers, when we start to bring in advanced meshing that we traditionally didn't have access to inside of SOLIDWORKS. Hexahedral and brick elements, we can do multi-step simulations as well. But when we step to the next level of structural performance engineer, this is really where the nonlinear and linear dynamic solvers of Abacus come into play. Highly nonlinear stuff, material failure, advanced connectors. Really, the default connection or interaction between bodies is real-world sliding contact, and everything is treated as nonlinear by default. And there's one level higher than there, structural mechanics engineer, where you get the explicit dynamic solver of Abacus. You can literally do car crashes in this level of software. If you see the word durability on here, durability and performance engineer, it simply means we're adding fatigue capabilities as well. Let me simplify this a little bit. If you think of the 4 steps here, when you get to structural performance engineer is where you get the nonlinear solver from Abacus. If you use the term durability, you get fatigue. When you get to structural mechanics engineer, you get that explicit dynamic solver of Abacus, and same for fatigue. So let's get hands-on with this stuff. How does it really look? And I want to take you on the journey of Resonant, a company that's been using SOLIDWORKS since the very beginning. They were founded back in 1989, headquartered in Lima, Peru, and they're one of the largest global manufacturers of underground mining and drilling equipment. They spend a good amount of revenue, though, on product failures and warranty claims, and they wanted to get into a higher level of software to basically improve their brand recognition and dramatically decrease the cost of warranty claims. So how does this look like from a SOLIDWORKS user? Well, you got to do a few things. The first is we're simply going to install the connector called Collaborative Designer for SOLIDWORKS into our SOLIDWORKS environment. So we log into our cloud platform and kick off this installation, just like any simulation add-in or any add-in to SOLIDWORKS. Then we're going to launch this from our platform as well. Clicking the platform actually launches up SOLIDWORKS so you can open your files locally as you normally would. Once they're open here, if you have a simulation set up, you can reuse some of that, or you can start fresh. We simply need to open our geometry and get it saved up into the cloud. Now this is your private platform. Nobody can access these files except for you. So it's really nice to use as a data management tool as well because it understands CAD references, shows everyone who's working on what at what time. You can do all the revision control, or if you're just doing sim, simply right-click in your task pane and hit save. Not only does it give you all that data management functionality so you can access your files from anywhere, but it takes care of the data translation. You can see the green checks in this convert status, so it's preparing it to be opened up on the Simulia side. Now this interface you're seeing right here is the locally installed simulation interface. It's the native app for Simulia. We're simply opening up that same SOLIDWORKS file now over here ready to start a simulation. That's as hard as it is to make a parametric link between SOLIDWORKS and very advanced simulation software. Right-click in the task pane and save it up. All right, that's the easy part. I guess the hard part would be actually creating our simulation, which we're going to do in 3 steps. One, we're going to create our simulation model. This might be called our finite element representation. We're going to tell it what mesh we want to use, what materials we're using, how things are connected. Then we'll get into the actual scenario creation of our loads and fixtures, and then of course review the results. So let's start off with simulation modeling. We need to set up our bodies, create materials and assign them to them, our mesh, and get them all connected. And this isn't a small simulation. A huge material library is supplied with Simulia with extensive behaviors not available in SOLIDWORKS. But applying them to the model is just as easy with a pretty familiar looking tree structure. Of course, meshing capabilities is one of the huge reasons to look at Simulia, where all sorts of element types and formulations are available. Since we have such similar components, we can really speed things up by creating a mesh rule, which captures the mesh size and settings we'd like to use for all sorts of plate steel. I can then reuse this by searching this mesh rule up because it's saved in our database just like our parts, and I can apply it to multiple, or in this case, pretty much all the parts in the assembly. This is a great way to get into advanced meshing, but still save time applying it to multiple components when you deal with similar geometry. Of course, we can set up rules that work globally like this, or we have full local mesh control as well. In this case, I'm just searching it up and applying my mesh rule to every single body, and by clicking Update, my mesh will be generated component by component, taking just a few minutes to mesh every part in this assembly. This mesh is saved inside of that finite element model for these parts that I mentioned, which also means if I reuse these in other simulations in the future, they're already going to know the information they need to mesh And if I reuse this assembly, let's say in a higher level assembly, how they're connected and what materials can be reused as well, making future simulations even faster. And really, I want to drive this point home because at any point in this process, I can always switch back to SOLIDWORKS and make a design change like a distance mate here. To get that to update and flow, all I need to do again is right click and save in the task pane of SOLIDWORKS, and everything will update on the Simulia side. Now we've got materials and mesh. Let's connect this stuff together. There's quite a few bolted connections in this design, and a virtual bolt can capture real-world conditions such as preload, bolt strength, all of this while reducing solve time because we don't actually have to mesh or deal with the contact between that bolt and its thread engagement. And we can also replicate this based on geometry. This is really cool because the replication tool is not relying on a pattern or a SOLIDWORKS feature in its tree. It's simply looking at the shape of the geometry and determining where similar bolts might be applied, saving us the hassle and all the clicks. All right, very similar to bolts here, there's some connections to linear actuators that we've omitted. They're not modeled in here, and I want to create a translator connector to mimic the behavior of these actuators. The connection between the main boom and the bracket that actually raises and lowers this boom. This is another great way to simplify the geometry for simulation without compromising on the physics. We can even include information like damping to get an extremely realistic behavior between the connection points. Here, let's add in some structural damping in the X direction, and I'm actually going to do this process twice, one for each side of the boom arm. All right, now that my connection's in place, a similar application could be to create a coupling. A coupling simply groups together mesh elements on a face to a single point in space. So I can do whatever I need to in the scenario with them grouped together. In this case, I'm going to couple the end face of the boom to a single point. Later on, I can create a remote load that applies just to that point, which would be equivalent to the weight of the machine equipment supported on that face. All sorts of other connections can be created or automatically searched for, and there's managers like a feature manager or a connection manager that's a convenient way to review all of them. You've just seen how to save designs from SOLIDWORKS into 3D Experience and prepare the bodies for simulation with the Simulia toolsets, assigning materials, meshing, and creating connections. Now it's time to move on into the next step of actually working with our scenario, creating the analysis steps, applying our loads, and our restraints onto the model. Luckily, the user interface doesn't really change that much. We just choose the Model Scenario Creation app from under the compass, and the tools of that app are now available in the action bar at the bottom. We need a finite element model to use in the simulation, and since we just created one in our last steps, we can choose it from the list and you're ready to go. That's how you can reuse all of that mesh work and material work in all sorts of simulations. Now we'll start with a nonlinear static step and review the step size for the solver. In fact, every simulation that is run in Simulia is nonlinear, so we'll ultimately want an explicit dynamic and fatigue outputs as well. You may have noticed earlier that while we defined some connections, we did not define how each component was contacting its neighbor. By default, this is going to be sliding real-world contact, but I want to be more realistic by creating a contact property that includes friction. We can then use that contact detection tool to look over the whole model. In this case, find any face pairs that are within 1/10 of a millimeter of each other and quickly apply that contact property with a single click. Of course, we need to define our connection to the real world, and a restraint fixing displacement in the X direction on the bottom face should be enough to hold this in place. The loading here is going to be a remote force applied on the point in space that we coupled with the end face of the boom, which needs to support about 2,200 pounds in the negative Y direction. I'll just choose the coupling, type in the load, and it's one of the fastest things to apply. And since we've got more than one load case, it makes sense to just duplicate all of this work for speed. This way we're confident we have an identical setup and only need to modify the loading, which is as easy as double-clicking the load from the feature manager. Now we've got our additional load case set up. Finally, we need to see the effects of both loading scenarios on the fatigue life of the assembly, which is called a durability case. Simulia handles both low and high cycle fatigue, and we just need to set up our cases as zero-based loading. Pretty quick. And before running the simulation, we can also kick off a series of model and scenario checks to ensure that we won't get any failures due to a misstep or a problem with our setup. This way we can catch mistakes without sacrificing solve time or taking a trial and error approach. This is particularly important if you're deciding to solve on cloud, where you can even expend some credits to unlock up to 144 cores of high performance computing. I definitely want to run the checks first and make sure everything's going to solve or at least not fail due to my mistakes by running those when I kick that off. Now, built in, you're going to get up to 8 cores of solving, whether it's locally, on cloud, as much as you want. So might as well send it to cloud and make their CPUs do the job. So you've just seen how to go from the initial setup of your finite element model to your scenario, add the loads, add the restraints, and actually kick off the solves as well. We've set up a couple of different load cases and set things up for durability and fatigue. Let's see what comes out of this at the end of the day. The main KPIs that we want to review here are the von Mises stress and log life of values. How long does it survive? Here we note the location of the maximum stress, and we can investigate a bit more with a response plot at that location. Very similarly, I want to review the displacement plots as well. Maximum displacement and maximum stress are where we expected. Values are a little bit high, but the trends make sense. So let's also take a look at the fatigue results. Here I simply need to make sure that my minimum log life is going to be long enough. Right now we've got values of about 5.86, which is actually not good enough. So I'm going to create sensors to track these. I know they're in the right positions. I want to make some design changes now, and sensors simply give me a real-time measurement that give me the number and could be used for optimization. So right now we've seen our results and we find out our actual is a little bit below our required, both in fatigue and in simulation. Not really good enough, so I need to make a design change. And as a SOLIDWORKS user, that's easy enough, but it's possible that who's running this software may be just wearing an analyst hat and doesn't use SOLIDWORKS and just does the simulation. Well, we can actually expose some dimensions to this person and control what they're allowed to change. Or we can task our design engineer to actually get back into the assembly and make the change. If you've got SOLIDWORKS, that's probably the easiest thing to do. But I'm going to show you how to give these dimensions to the analyst. So the designer inside of SOLIDWORKS can say, I'm going to allow you to move these key dimensions and nothing else. How can we actually expose so they can make a change to our SOLIDWORKS model without being inside of SOLIDWORKS? Well, the first step is to just go back to SOLIDWORKS and get the geometry open. It's saved into my cloud tool, so I'm just going to search it up and open it from the cloud platform. So I know I've always got the latest and greatest data, maybe working from home this day. Here we're going to do this on the part itself. So I'll open this up and capture the key dimensions as parameters. If you've ever used optimization in SOLIDWORKS Simulation Professional, this is the exact same tools. Simply open up parameters, choose the dimensions that we want to expose to the analyst on the Simulia side, and give them a name. Next, of course, we need to reserve the geometry. Lock it or check it out, which gives us the right access in our data management system, and simply save it back up to the platform. Once this is saved up, of course, all of our changes and the data management tool that takes care of the translation for us, so any of this can be seen on the Simulia side. To bring in these design parameters, we simply need to access the parametric bridge tool. And if the parameters have been defined in SOLIDWORKS like we just did, they're going to get pulled right into the tree here in Simulia. Not only are we going to be able to see the dimensions, but we can physically change them in the model. That means we can make our guesses as an analyst on those, or actually set them up to be optimized by the software. So there's nothing left to do but rerun the simulation and the newly edited design and check the key results to see if our sensors now show us some good numbers. And in this case, I can tell you our simulation results are going to come out okay. We'll be able to reduce the amount of deflection, reduce our stress using our sensor to know we're under 250 megapascals, and also improve the fatigue life. Ultimately, we got just to the fatigue lifespan that we needed and under our individual stress. At this point, you've seen the handshake between SOLIDWORKS and 3D Experience multiple times, allowing anyone in the company to access the data they need from any location with an internet connection. We've gone through the steps of setting up the simulation model, creating and running the scenario, actually optimizing our design, and reviewing the results to make sure that we meet what Resoman needed to protect their brand. From a technical perspective, that means using simulation as a design tool, just as we always have with SOLIDWORKS, but now with more power ultimately leading to better quality designs. We're taking advantage of cloud computing and storage, which simply increases the overall efficiency of the process. And from a business point of view, a completely connected set of tools increases team collaboration and leads to a more innovative product. Not only is the overall engineering cycle time reduced, but IT overhead and infrastructure costs are effectively eliminated. For Resoman, these advanced sim capabilities led to reduced warranty costs, reduced recalls, better fatigue performance, and ultimately enhanced brand recognition and value overall. I hope this gives you an idea of how you can take your SOLIDWORKS designs and simulations to the next level, and of course, continue to work in a completely connected design workflow.